In this video, we are going to talk about capacitors, which are energy storage elements. So they're a little bit different from resistors. What is a capacitor? Well, we are going to look at a parallel plate capacitor, which is the simplest type of capacitor. And imagine I have two plates and they are very close together. And what I'm going to do is I'm going to move one positive charge to one plate. And to keep the whole thing neutral, I'm going to take one charge away from the other side. So I have a negative charge on the right side plate. And I'm going to repeat this. I'm going to add one more charge, take one more away. And as I'm doing this process, what's actually happening is that there is going to be an electrical field between these two plates that's being established. And the more charge I put on these plates, the stronger my electrical field. And my electrical field relates to voltage. Because remember, voltage was the amount of work it took to move a positive charge from one side to another. And there's actually going to be a voltage in this direction because it's going to take effort to move a positive charge. If I would take a fictitious charge here and I would need to move it from one side of the plate to the other, I would have to move against this electrical field. These plates are not touching, so I can't actually move a charge. But remember, voltage is just an indication of what it would take if I would have a charge and I move it against an electrical field, for example. How much effort it takes to go from one side to the other. So what this means is that there is a relationship between the voltage across a capacitor and how much charge is actually stored on that capacitor. And that equation is given here. So this relates the amount of charge and the voltage. And there is this constant C called the capacitance of the capacitor. And a way to visualize, or as an analogy to my capacitor, is basically this bucket. A capacitor, you can see it as a charge bucket. The more charge is in there, the higher the voltage. Let's look at what is this capacitance. Well, the capacitance of a capacitor depends on the physical dimensions of the capacitor. It depends on the area, A, the distance between the plates, D, and then a physical constant called the dielectric constant. And this is basically a material property of whatever is in between those plates. There isn't actually any charge moving from one plate to the other. I'm just putting charge on one side and taking it away on the other. And so in between is an insulator that does not conduct any charge. The unit of capacitance is called the farad, in memory of Michael Faraday. And an important thing to note is that typical values of capacitors are in the range of micro to picofarads, so very, very small. Okay, so now let's do the following. Imagine you're an observer here, and as I was passing charges onto this capacitor, I saw charges passing by, and charges passing by is current, right? So the current, like my normal definition of current, is just the amount of charge per unit of time. And so I have actually a current that's dumping charge on my capacitor. Or equivalently, I can express my charge on my capacitor as a function of current. So these two equations are obviously related. What's important to see, though, is that the current on both sides is the same, because every time I put a charge on one side, I'm taking a charge away from the other side. Let's look at my capacitor again, and this is the symbol I'm going to use for a capacitor. What's important is that this current is the same on both sides, even though technically charge does not jump between those two plates. Every time I put a charge on one side, I'm taking one away from the other side, and so these two currents on both sides are equal. And I can use these equations to find the equation how current actually relates to voltage for a capacitor. So if I combine these two, I see that the current that goes through my capacitor, and again, it doesn't exactly go through because there's an insulator in between, so charges don't jump, but I can look at the current on one side and the other, and it's the same. That current is given by this equation here, and it depends on the change of voltage over time, because the voltage relates to charge, and the change of charge over time is related to the current. So this is a really important equation that relates voltage and current for a capacitor. This is very different from a resistor, right? So the current depends on the change of voltage. And I can also then express voltage as a function of current, so this becomes now this integral. And you see that I actually need to know what's happening all the way back to time minus infinity. Well, it's easier to split up this integral in two parts, from minus infinity to a certain time t0, and then from t0 onwards. And I assume that basically this part I know. So I'm going to start off with the known voltage, and I'm going to see what the progression is from that point onwards. So in that case, I don't need to know everything that happened before. I don't need to go all the way back to time minus infinity. There are actually a few different symbols for capacitors. This is the one we've seen already. For electrolytic capacitors, you add this plus sign because these capacitors are not symmetric, so you know which part has to go to the higher voltage. And then you also have potentially variable capacitors. An important thing to note, though, is that a capacitor is also a linear element. So it's not just resistors. Capacitors are another example of linear elements. So now let's apply this and let's look at an example. So imagine I have my capacitor here and the current is given by this function here. Current varies in time. What is the capacitor voltage going to do? Well, I can use this equation, and what the capacitor voltage is going to be the integral of this current. And I have between time 0 and 1 a linear current, so this is going to be a quadratic equation in terms of the voltage. And then the current suddenly goes negative, and that means that the voltage is going to drop. And the voltage drop is going to be linear because the current between 1 and 2 is constant. So what is happening is, here I'm charging the capacitor, I'm putting charges on there, and then, so I'm dumping charge, and then the current goes negative, then I'm taking charges away. This is called discharging the capacitor. Okay, let's look at another example. Now I'm connecting a voltage source over my capacitor, so I'm forcing the voltage to be a certain value. Well, in that case, if I know the voltage, I can calculate the current, and it's just the derivative. So my current is going to be 1 here. What happens then at time equal to 1? Okay, I take the derivative. My current is going to go to minus infinity, and then between 1 and 2, the voltage is constant, and so my current is going to be 0. Current equal to minus infinity. This is actually not physically possible. There's no way an actual source can deliver this much current. So we say that really for a capacitor, this isn't possible. For a capacitor, the voltage cannot change instantaneously. And this is a really, really important property of a capacitor. For a capacitor, the voltage cannot change instantaneously. So the voltage curve for a capacitor always has to be continuous. And it basically just follows from the fact that you don't want to have an infinite current. You can't really have an infinite current. Okay, so now let's look at the power consumption of a capacitor. We see that we are using again the passive sign convention, right, as we did for resistors. And the power is V times I. I can look now at how much energy is stored on a capacitor, which is nothing more than the integral of power. So I just look at how much power is supplied to my capacitor, or my capacitor is receiving. So the total energy of my capacitor is just the integral of how much power it received over time. I plug in power is V times I, and then I can use this equation, simplify, and I get the following expression. And I'm going to assume that at times t is equal to minus infinity, my capacitor is discharged. And so I see that at any point in time, the energy stored in my capacitor is given by this equation here. So you can express it either as a function of the voltage or as a function of the charge, because remember, the charge and the voltage are linearly related. So the voltage is a direct indication of how much charge is on the capacitor. So by storing charge on the capacitor, I'm actually storing energy. This is why this is called an energy storage element. we can also see this from this behavior of the capacitor. So imagine I have a voltage source, and between time 0 and 1, my voltage is linearly increasing. So that means if I look at this equation, I have my current, which is constant. And then at time t equal to 1, I'm going to disconnect my capacitor from my source. So my capacitor is going to basically be by itself. What's going to happen now? Well, I know that the current has to be equal to 0. Right? There's nothing connected to it. There cannot be any current flowing. So I know my current is going to drop to 0. If my current drops to 0 from this equation, I see that my voltage is going to remain constant. So my capacitor is actually storing the charge. It's keeping the voltage constant. And then, at time equal to 2, I'm going to connect a resistor. What's happening then? Well, there was some charge in this capacitor. It's going to start leaking away. And when it's leaking away, the voltage is going to drop. And the result is going to be a current. Remember, this current was positive in this direction because we were using the passive sign convention. Right? So this is a negative current. And so this corresponds to the capacitor being discharged. Now, the exact shape of this curve at this point when it's discharging, we will discuss in a later video when we are actually going to analyze these kind of circuits with capacitors and resistors. Okay, so let's summarize. What do we know about capacitors? Capacitors are such that the voltage over the capacitor cannot change instantaneously. So that means that the voltage curve of a capacitor always has to be continuous. This is a very, very important property of a capacitor. Also, a capacitor is an energy or charge storage element. If there is no current, then the voltage remains constant. And the final important property is that a capacitor has memory. It depends on the past. What's happening to a capacitor depends on the past. So, these are the basic things you need to know about capacitors. In the next video, we're going to talk about another energy storage element, inductor, and then we're going to look at how capacitors actually behave in circuits.